Hello everyone, in this lecture we are going to look at the proton NMR spectroscopy, which is a super useful and powerful tool to help you identify the structure of certain organic molecules. And what you are seeing on this screen is a very typical proton NMR spectrum. What you see here, there are some peaks that's going up, right? Signal going up, and you see the numbers at the bottom of this spectrum going from the lower number to higher number, and it's so-called chemical shift. Usually you will see the ppm right here. We'll explain what are those later on. And when you look at a proton spectrum, there are a few terms that you should be very familiar with. The first term is so-called downfield and upfield. So downfield is on the left side of the spectrum, that's related to a higher energy level. And on the right, it is opposite, is upfield, and that is a lower energy level. And sometimes you will hear the upfield shift or downfield shift. That means either downfield shift to the left, that means the signal going to the left a little more. And if upfield shift, the signal going to the right side a little more. And also another way to talk about NMR in terms of the position of the signal is that sometimes on the downfield shift, that is the D shield position. What does that even mean? Okay, what we are looking at here is that the electron around the proton we are looking at, if it's D shield, means that there are less electrons. What does electron do? Okay, because electron spin, right? That means that because it's less electron density on there, that means more magnetic field will act on the proton because it needs more energy right there. And for the upfield shift, the one on the right, usually it's a shield. What does that mean? Okay, that means around that certain proton you are looking at, there are more electron density around this proton that shield this proton, because when the electron spin, that will create the opposite position of the magnetic field. So that means at this moment, now you have less magnetic force come from the machine that act on the proton. That means this proton actually needs less energy. So that is the proton that have more electron density around it, then it will be shielded. It will have a upfield shift, which means that signal will be more on the right side of the NMR spectrum. So that is our NMR spectrum, some terminology that you need to be familiar with. The second thing we want to talk about here is how the proton NMR spectroscopy can help us to identify or figure out what is the structure of the molecule. So on a proton NMR, there are 4 characteristics that can help us. The first characteristic is the number of signals. The second is the signal integration. And the third one is where the signal at, the signal location on the spectrum, and we call it chemical shift. What you see here right at the bottom of this spectrum is that chemical shift, ppm, that is where specifically signal located that relate to the energy, also relate to the electron density electronic environment around this proton. And then the last will be how the signal looks like, the signal shape. We call it splitting pattern. If we are looking at this proton NMR spectrum right here, right, we see, okay, this signal kind of here, and this signal right here, and this some messed up peak right here, that is showing you there are different protons, different number of signals, and also under the signal, this is different from proton NMR versus the IR, right? IR signal going down, proton NMR signal going up. So under all these signals, the integration will also tell us information about the protons. And all these signals have at different locations, that is chemical shift and the shape, right? You see this one is a small peak, a big peak, and small peak. This one has 4 peaks inside. What that can tell us, that is all the characteristics of a NMR, proton NMR, that will help us to figure out what is the structure of the molecule. So today, in this lecture, what we are going to focus on is the number of signals and the signal integration. What kind of information we can get from all these 2 characteristics of proton NMR. Let's get started. The first characteristic of the proton NMR is the number of signals. In general, number of signals indicate the number of different protons. So what does different proton mean? Here, different proton means the proton in different electronic environment. Sometimes you will hear that the protons with unique electron environment, that means they are unique protons. And each proton that's unique from each other, then they will give you a signal. Okay, so then if those protons are the same or identical in NMR, identical proton, that means their electronic environment are the same. Sometimes you also hear this word chemically equivalent. So the first question you may have is, how do I know if these 2 protons we are looking at, they are the identical protons chemically equivalent or not? So there are the ways to see them. So the first type of the identical protons, we call it homotopic protons. So homotopic protons are the protons that have an axis of rotational symmetry. Okay, what does that mean? I'm going to give you one example. For example, if we are looking at these protons on this molecule, if we specifically looking at the blue molecule and blue hydrogen and red hydrogen, right? If you rotate this carbon-chlorine bond, right? You rotate 120 degrees, then the red hydrogen will be to the blue hydrogen, and blue hydrogen will be to the black position, and then black will be red. So theoretically, all these 3, you rotate every 120 degrees, they will sit exactly in the same electronic environment. So they are having a rotational symmetry. So they are all homotopic protons. I'm going to give you another example. For example, if we are looking at this proton right here, so this proton, the red proton, and then blue proton. Now what we are looking at here, imagine if you rotate this molecule 180 degrees, this hydrogen, this blue hydrogen and the red hydrogen, they will be in exactly the same electronic environment. environment. So they also have the rotational symmetry. They are homotopic protons. The second type of identical protons we are looking at here is so-called anisotropy protons. So we cannot hear this word before, anisotropy, right? Anisotropy means a pair of molecules that mirror image to each other. So anisotropy protons, they are in the molecule that they are mirror image to each other. So that means in this type of molecule, this molecule need to have a plane of reflection, right? It needs to have a reflection plane inside this molecule. So that can make one proton to be mirror image to another. I'm going to give you one example right here. So if we are looking at a molecule like this. Okay, this is a benzene ring. What I'm going to do here is I'm going to put a methyl group right here. And now what we are looking at is this red proton and this blue proton. So in this molecule, okay, this is toluene. In this molecule, you can find this mirror plane. And to this mirror plane inside this molecule, what we see here is this hydrogen and this blue hydrogen, they are mirror image to each other. So by the definition, the blue hydrogen and the red hydrogen, they are anisotropy protons. They are identical protons. That means they give the same signal, give only one signal, right, inside the proton NMR. Let's look at another example. So if we have this molecule right here, and chlorine, and we have this red hydrogen and blue hydrogen. So in this case, we still can find a reflect plane inside this molecule, because this molecule actually is not chiral molecule, right? So we can find this plane that goes through this carbon and this fluorine and chlorine. So in this case, the red hydrogen and the blue hydrogen, they are mirror image to each other, so they are also anisotropy proton. Now we know how to identify the identical protons. So basically, we can go through this chart, right? We are looking for the axis rotational symmetry. If we have the rotational symmetry, then they are all homotopic protons. If there are no axis rotational symmetry, then we are looking at the plane, right? If you can find a reflection plane inside this molecule, that two protons you are looking at that mirror image to each other through that plane, then yes, that is anisotropy protons. Then we get here is they are identical protons. Identical protons give only one signal, so they give the same signal. That is, we end up with one signal. If the answer here is no, right, you cannot find reflect plane for the proton to be mirror image to each other, then all the proton you are looking at is not chemically equivalent, then you will get signal for each of the protons you are looking at. And the question here is, how do we know if they are anisotropy proton, homotopic protons, or they are different protons? There are a way to do it. That is the skill that you need to build, is that you can use a so-called replacement test. Okay. For example, if we start with a molecule, we already see this molecule earlier, and we will replace one of the proton with an X. So if we replace the red with an X, and keep blue, and versus if we replace the blue one with X and keep red, okay? If this replacement of these two protons you are looking at, that give you exactly same compound or same molecule, then that means this blue hydrogen and the red hydrogen, they are homotopic. They are identical. Now if we are looking at, for example, this molecule right here, we have this red hydrogen, blue hydrogen, and we have fluorine and chlorine. And now we are going to replace hydrogen with X, the red one first. We replace it with X and leave the blue one as it is. And versus if we replace the blue one with X and leave the red one. Okay, so what we are getting here now, if you can see this, you will see, if you put a mirror here, these two molecules that you are getting by replacement give you a pair of enantiomer. So this is a pair of enantiomer. That means the hydrogen we are looking at here, the blue and the red hydrogen, they are enantiotopic protons. So now you may have a question, what if we do the replacement test and we got Dow's stereomers? So for example, if we start with this molecule right here, what I'm going to put here is a chlorine. So that means what we are looking at here now, this is a chiral center, right? This is a chiral center. And what we are going to look is this hydrogen right here and this hydrogen right here. Okay, let's do the test. So first of all, I'm going to replace the red one with a X, okay? So if I have a X right here, okay, I'm going to draw this into a bond line. Okay, this is X, and we will have blue, versus if we replace the blue with X, right? So we'll have here, and we have the red hydrogen as it is, and the blue hydrogen replaced by X. So what we are getting here now is a Dow stereomer. Okay, so when we get a Dow stereomer, that means these two hydrogen, the red hydrogen and blue hydrogen, they are not in the equivalent environment. That means they are different protons, and specifically what they are called here, okay, it's called Dow stereotopic protons. Dow stereotopic protons are basically different protons, okay, different protons. That means they will give off different signals in the proton NMR. So they belong to this part here, not equivalent. They will give you two signals. Okay, each type of proton will give you one signal. So that is how we can determine how many signals we are going to see based on how many different type of protons we'll see. Now let's apply the skill we just learned to identify what type of the protons one to the other, the relationship between those two highlighted protons on each of the molecule, based on if they are homotopic protons, enantiotopic protons, or stereotopic protons. And for question A, what we can do is we can go to the chart, right? Axis, yes or no, and then the plane, yes or no. Or we can use the replacement test. What I will do here is I will use the replacement test. So what I will do here is first I will replace one of these back hydrogens with an X and keep the front as it is. Versus if I replace the front one with an X and the back with our hydrogen as it is. So what we are seeing here now, this is become a chiral center, and that give you a pair of enantiomer. So now we know that this is enantiotopic protons, and they will only give you one signal. They are the identical protons or chemically equivalent protons. Now let's look at another example. Let's look at molecule N. So in molecule N right here, there are two ways we can look at it. Let's use another way. So another way is we're going to see if there is rotational symmetry for the two hydrogens. Okay, so if we do this axis, we rotate this molecule 180 degrees. Let's see what we get there. That means what we get is exactly what we see here. So if we highlight this hydrogen as a blue hydrogen, now this blue hydrogen actually will go back, and the front hydrogen is that red hydrogen right here, and give you the same molecule. That means that this blue hydrogen and red hydrogen, they are exactly the same. They have the rotational symmetry, so that means they are homotopic protons. In another word, they will only give one signal because they are chemically equivalent proton in this molecule. So now I would like you to pause the video and work on the other examples right here and come back to check the answer key. The second characteristic of proton NMR is integration of the signals. Specifically, it means the area under the signals that is integral. That is related to the relative number of protons that giving rise to that signal. So if we are looking at this example here, this is a proton NMR. So usually you will see some signs look like this, that is integral, taking integral. So the number right here is 2740.2, 28.4, and 42.2. But probably in this molecule, that means that they absolutely have 27 proton to give this signal, 40 to give this signal. What we will do here is we will take in a ratio. So if you divide all this number by the smallest number of all, so we consider this as 1, right? Divide by 27, you give 1 and about 1.5, 1 and 1.5. That means the proton number to give all these signals right here, 4 different signals, that ratio is 1 to 1.5 to 1 to 1.5. And if you are looking at the molecule, probably this molecule can have this type of proton, 2 of them, 3 of them, 2 of this, and 3 of this. So that integration number right here is just a relative number of protons, the ratio between them. So the message here is integration a relative quantity rather than an absolute count of the number of protons for each signal. So it's just a relative ratio of each type of protons that with unique electronic environment. Now let's look at one example to explain what does the integration really tell us. So for example, this proton NMR spectrum is for this molecule. It's a ketone right here. So in this molecule, immediately you can tell from what we just learned today is that there are some equivalent hydrogens. So first equivalent hydrogens are these hydrogens on the CH2. Okay. The left two and the right two, they are enantiotopic protons because they are mirror image to each other. And they will rise the exactly same signal, so they are the same ones. And then what we see here is all these hydrogens on the methyl group, because imagine if you are rotating this sigma bond, right? All these three hydrogens, they have rotary symmetry, and the one on the left, this three and this three, they are mirror image to each other, then they are anechotopic protons. So all in all, they are all same protons. That means for this molecule, what we are looking at here is it will have two different type of protons which have different electronic environment. So we will have two signals. And from integration ratio, we are looking at 32 and 48. If divided by smallest number is 1 to 1.5, so it's 2 to 3 ratio. So the ratio here, if I do the integral, is 2 and 3. Okay, that basically tell you that this type of proton that raise this signal compared to the number of the proton to raise up this signal is 2 to 3. However, if we are looking at this molecule, right? Here, there are 4 to 6. So the ratio here, the absolute count is 4 to 6. And the integral ratio is 2 to 3. So that tells you that the integration ratio here is tell you a relative quantity rather than the absolute count of the number of protons, which rise up the signals that showing on the proton NMR. Now let's combine these two characteristics together, the skill that we just built to solve some problem. So this type of problem is, I just give you a molecule, right? The question here is how many signal will be expected on a proton NMR spectrum. And also for the integral ratio, what is the integral ratio between the signals that will be expected on the NMR? So let's look at the first example. So first one is the butane. So for butane, okay, so if you are thinking about the molecule right here, basically what we can see, this molecule is very symmetric, right? And you will have all these methyl hydrogens. The reason why I put them in blue, because they are all the same hydrogens, because this molecule is symmetric, right? If you think about, there is a rotational symmetry kind of down this way, and you rotate 180 degrees. First of all, these two methyl groups will replace each other, right? You get that rotational symmetry, so that means these two methyl groups, they are equivalent, and all the hydrogens on there should be equivalent. And then all these hydrogens on each of the methyl, because they have this rotational symmetry, let's draw another rotation through this sigma bond 120. Every single time you rotate 120, the hydrogen will replace the other. So that is rotational symmetry. So that means all these 6 hydrogens, they are the same hydrogens. They are giving the same signals as one signal. So they are chemically equivalent. And so as the CH2 and this CH2, so we need to be able to see, right? There are hydrogens on here. So these 4 hydrogens, they are chemically equivalent. They will give the same signal. So what we will see here is, for this molecule butane, you will have 2 signals on the proton NMR, and the signal ratio, the absolute count is 4 to 6. And the ratio will be 2 to 3. Okay, 2 to 3. So this is the absolute count. Number of proton ratio. Okay. So let's look at a little more complicated situation. Now we are looking at this molecule right here. Okay. So for this molecule, first of all, this molecule looks like it have a plane symmetry inside this molecule, okay? So that means whatever on this side, if this is hydrogen, then it will have an anechotopic proton with it. Now the second skill we need to practice on here is that we need to be able to see there are protons on this molecule. So first set of proton is, again, all these hydrogens on methyl. I will draw them out, okay? So they are mirror image to each other. So they are this set and this set, they are anechotopic protons, and each of these hydrogens on the methyl, they are homotopic protons. So all in all, they are all same protons. And then second protons we are seeing here is this hydrogen that is on that plane, so it by itself. And then we have these two red hydrogens that they are mirror image to each other, that anechotopic protons. And then there are one more proton right on this. Okay, so 4 different colors, 4 signals, 4 different protons. And the ratio, if we start from the blue one will be 6, and then you have 2 of red and 1 of green and 1 of yellow. So the ratio here is 6 to 2 to 1 to 1. Okay, so the next one is a little more complicated. I'm going to draw out this molecule right here, but I want you to work on it by yourself to see if you can see all the protons first, and then determine what kind of relationships they are, if they are electronic environment equivalent, or they are different protons. So you can pause the video right here and work on this problem. Okay, welcome back. So if we are looking at this molecule, first of all, I'm just going to use numbers. Remember it that there will be protons right here, right? I will say proton 1. How many? 3 of them. And the second one will be 2, 3, and 4, and 5, and 6, and 7. Okay. And why? Because there is no reflection plane in this molecule. This molecule is asymmetric. So all these protons, they are now be able to be anechotopic protons. And now let's look at for proton A, that is for methyl. Methyl has 3 protons, that homotopic protons. So first of all, if I just say 1, 2, 3, 4, 5, 6, 7. Okay, this number indicates the protons assigned to these protons. Okay, this is proton 1, and you have 3 of them. So I will say 3 hydrogens. And for proton 2, there are only 1. And for proton 3, only 1. And 4 is 1 and 1. Maybe I should put a number right here. 5, you have 1. And 6, you have 2. And 7, you have 3. So the ratio here will be 3 to 1 to 1 to 1 to 1 to 1, 2, and 3. So these are the 2 characteristics of proton NMR, the information that we can use to identify the structure or the features of the molecule. So this is the end of this video. You do have a practice set you can practice on, and I will see you guys in class.